A driverless car is sometimes called a self-driving car. It is an automated car or an autonomous vehicle that is robotic and designed to travel between destinations without a human operator. There are a lot of questions being asked about autonomous vehicles. For instance, how will the law handle driverless cars? How do they use hardware and software to travel the road? What safety concerns do people have regarding driverless cars? Which companies are leading the way in autonomous vehicle technology? And what are the overall benefits of driverless car technology to consumers and businesses?
Autonomous vehicles are considered to be one of the most exciting inventions in the automotive industry so far, and as the technology continues to develop, it is necessary for the state and municipal governments to address the potential impact of these vehicles on the road. Developing opinion of autonomous vehicle technology has sparked concerns of security and safety. Legislation related to self-driving vehicles was first introduced in the state of Nevada in 2011, which declared only the intent to encourage the safe development, testing, and operation of self-driving vehicles. Furthermore, it became the opinion of Nevada legislators that technology should not specifically be prohibited nor specifically regulated for the testing or operation of autonomous technology of motor vehicles in public transit. Since 2011, 16 states have followed the regulations set forth by the state of Nevada and have introduced legislation related to autonomous vehicles, allowing self-driving vehicles to be openly tested on public streets. In California specifically, the post-testing development of autonomous vehicles is currently under development. Although current legislation does not specifically regulate driver-free vehicles, preceding regulations will instead address specific safety requirements. Manufacturers will need to meet and certify that their vehicles have successfully been tested, meet certain safety requirements, and are ready for the general public to operate. The ultimate goal of California legislatures is not to regulate the driver-free system, but instead regulate specific security and safety concerns. Therefore, legislation seen in automotive components such as anti-lock brakes, sensors for parallel parking, and cruise control will serve as a template for future regulations.
Driverless cars use a variety of hardware components to provide information to a computer responsible for controlling the vehicle. LiDAR, light detection and ranging systems, provide detailed three-dimensional information about the car's surroundings. GPS, global positioning system, gives the location of the car. Radar and sonar provide fine-grained, short and mid-range information about obstacles near the vehicle. Cameras are used to recognize shapes and colors like stop signs and traffic lights. Other instruments like gyroscopes, altimeters, accelerometers, and tachometers provide precise information about the car and its systems. The most noticeable feature of any driverless car prototype is the LiDAR system. LiDAR is primarily a camera system that uses lasers to measure the distance to objects to allow the car to see its surroundings. LiDAR, which stands for light detection and ranging, is a remote sensing method that uses light in the form of a pulsed laser to measure ranges to objects and geographical features. These light pulses generate precise, three-dimensional information about the car's surroundings. The Global Positioning System, GPS, is a satellite-based navigation system made up of a network of 24 satellites placed in orbit by the U.S. Department of Defense. GPS was originally intended for military applications, but in the 1980s, the government made the system available for civilian use. GPS works in any weather conditions, anywhere in the world, 24 hours a day. GPS provides the car with its position on the Earth's surface with a best-case accuracy of 7.8 meters for civilian use. GPS also provides the car with an accurate altitude measurement. Driverless cars utilize front and rear-facing cameras to detect pedestrians, stoplights, and other information near the car. Google mounts regular cameras around the exterior of the car in pairs with a small separation between them. The overlapping fields of view create a parallax not unlike our own eyes. This allows the system to track an object's distance in real time. As long as it has been spotted by more than one camera, the car knows where it is. These stereo cameras have a 50-degree field of view, but are only accurate up to about 30 meters. Each driverless car is slightly different, but some of those tested have featured advanced sonar technology. The limitations of sonar are its narrow field of view and its relatively short effective range, about 6 meters. While LiDAR is great for accurately mapping surroundings, its one fatal flaw is its inability to accurately monitor the speed of surrounding vehicles in real time. Bumper-mounted radar units can pick up the slack. The radar units allow the car to avoid impact by sending a signal to the onboard computer to apply the brakes or move out of the way when applicable. The radar system is paired with sonar in at least some of Google's test cars. While radar works up to 200 meters away, sonar is only good for 6 meters. They both have a narrow field of view, so the car knows if another vehicle crosses the radar and sonar beams. This signal could be used to swerve, apply the brakes, or pre-tension seatbelts.
Driverless cars rely on a set of complex pieces of hardware to control their driving and navigation systems. In order to effectively maintain operation, they need software that gathers data from the respective hardware and processes the data efficiently. Driverless cars can accomplish this by utilizing their software to do the following tasks: real-time mapping, navigation and positioning, and proximity awareness. The vehicles utilize three-dimensional scans via LiDAR to provide real-time mapping. The information provided by the scan allows the driverless cars to provide an intensity model and a 360-degree view of the live environment. The intensity model allows the driverless cars to presume changes in the environment that may be unaccounted for by static mapping. Additionally, the information provided by the 360-degree view allows the operating system to integrate information provided by the other sensors more efficiently. In order to navigate effectively, driverless cars use GPS. Global positioning satellites help driverless cars with their position and navigation. The driverless car is able to process the data real time and ensure that the vehicle is on course and able to react to its environment. Furthermore, driverless cars need to be able to react instantaneously to the environment around them. In addition to real-time mapping and GPS, driverless cars need to be able to process data that makes them aware of their distance, speed, elevation, orientation, and a visual identification of their physical surroundings. The onboard computer processes data received by the car's radar and sonar, tachometer, altimeter, gyroscope, and cameras to achieve the desired result.
Driverless car technology has presented numerous concerns for safety, with the most prominent concerns being that all current software is unstable and could potentially crash or freeze, just like the software running our PCs. Also, many people cite the fear that their car could be hacked and taken over. Another potential problem is sharing the road with human-driven cars. How will a driverless car predict and react to the often irrational decisions made by human drivers? Map accuracy is not a problem when driverless cars are on the roads at home or in an urban setting. But what about traveling in unknown or rural areas where maps or GPS may be unreliable? Their sensors also have limited vision. Currently, their sensors cannot see in heavy rain or snow and cannot recognize potholes until they hit them. Driverless cars would eventually be put in a situation where they, meaning their software, would have to make a life or death decision. Driverless cars rely on their software to make decisions and guide the vehicle. A software glitch could potentially result in a fatal crash. Even the current Google test vehicles traversing our streets have a backup driver and a second person who monitors the car and can shut it down in case of an error. Creating fail-safe software for driverless vehicles will require an evolution in software design. Given the numerous media-covered cases of hacking, people are understandably concerned that their driverless car could be hacked and driven somewhere that they didn't direct it to go. The driverless cars being tested by Google have been involved in 11 minor accidents over the past 6 years. In all of those incidents, it was determined that a human-driven car caused the accident. One of the accidents was a fender bender, where the driverless car inched forward and then stopped abruptly, and the human-driven car behind it rear-ended it. Critics are asking if the driverless car may be perhaps too safe, not allowing for the real-life decisions that humans often make. Even Google admits it may need to adjust the driverless car software to act more like a human driver. Driverless car technology will have to evolve to be able to share the road with human beings. Google has great maps, but what about rural areas? Google has only created detailed maps for about 2,000 miles of the 4 million miles of United States roadways. Driverless car maps will have to evolve to be able to take their passengers on back road trips through less driven areas. Bad weather happens, often. If a driverless car's sensors are inefficient in heavy rain or snow, it simply will not be able to function adequately for everyday use. If the driverless car's sensors cannot see a pothole, it won't be able to slow down appropriately, and hitting a pothole at a high speed can cause a crash or loss of control. Whose safety will be the most important to a driverless car in a potential crash? Will a driverless car swerve and avoid a collision with a school bus filled with children, resulting in the death of its occupant? Or will it sacrifice the kids on the bus and save its occupants? Making decisions like these will be inevitable, and designing software that can make these life or death decisions may be the biggest challenge facing driverless vehicle technology.
Google is leading the pack when it comes to research on autonomous vehicles. Google started its self-driving car project in 2009 and has since passed the 1 million miles driving mark. Audi has built an autonomous driving Audi A7 that piloted itself 550 miles from Silicon Valley to Las Vegas. Another company making strides in the driverless vehicle research is Daimler. Daimler is currently working on the self-driving Freightliner Inspiration truck, the world's first autonomous vehicle to be granted a license for road use in the state of Nevada. Volvo is also working on an autonomous vehicle project called the IntelliSafe project, and it plans to start trials in 2017 by giving 100 customers IntelliSafe autopilot-equipped vehicles. Cisco is known for its technologies that wirelessly transport video and voice data around the world. These technologies can be further developed to help cars communicate with their surroundings, and will no doubt have a place in driverless cars. Intel's in-vehicle solutions are a family of hardware and software products designed to enable car makers and their suppliers to more quickly and easily deliver in-vehicle experiences that consumers demand. The family of products includes a range of compute modules, an integrated software stack of operating systems, plus middleware and development kits. Delphi's team of engineers, along with autonomous driving car they call Roadrunner, have completed their nearly 3,400-mile cross-country journey. The trip spanned across the southern United States, with the car successfully traveling from San Francisco, California to New York City, New York. NVIDIA is also a player in the driverless car market. To address the increased computation needs of cars, NVIDIA recently introduced the Tegra K1 mobile processor. It packs 10 times the computing power of its predecessors, and yet still operates in the same power envelope. NVIDIA has a long-standing relationship with many automakers including Audi, Volkswagen, BMW, and Tesla.
The consumer benefit of driverless cars will be immediately felt. Services like Uber disrupted the taxicab industry with their rideshare app. Their app brings a convenient, low-cost, stress-reducing alternative to driving oneself or using a cab. Uber is not stopping there. They are betting their future on making their ride service driverless. They have already partnered with the University of Arizona to cultivate the next generation of developers who will explore this new technology. In support of this, Arizona Governor Doug Ducey issued an executive order on August 25, 2015 that supports the testing and operation of self-driving vehicles in Arizona. A self-driving car can be more than just a convenience for the frazzled commuter. It can be a life-changing innovation for the elderly or disabled. Consider the improvement in quality of life a driverless car could mean for a blind person. In 2013, the population of people in the U.S. described as having a visual disability is 7.3 million. Add in the number of wheelchair-bound individuals, veterans who suffered amputations and lost the ability to drive, and the elderly who are unfit to drive. This is a significant population who would have increased access to mobility. Businesses stand to benefit greatly from self-driving vehicles. For example, the United States employs 3.5 million truck drivers. One statistic from 2006 reports that the transportation industry logged 432.9 billion miles. The American Transportation Research Institute estimates that congestion adds $9.2 billion in operating costs as a result of lost productivity. Self-driving technology will disrupt the transportation industry even more profoundly than Uber has disrupted the taxicab industry. In the big picture, driverless cars will radically change every aspect of our lives. The effect of having safer roads will reduce costs of societal harm by traffic collisions and fatalities. There will be reduced revenue from traffic tickets issued by law enforcement. The loss of jobs in trucking as the demand falls for a labor force of drivers will move to the new demand in manufacturing. The auto insurance industry will be upended as traffic collisions diminish. Finally, gas stations will become a relic, just like drivers' wanted signs and how am I driving bumper stickers, as cars will drive themselves to fuel up while not in use by humans.
Despite the numerous challenges presented in bringing fully autonomous vehicles into regular everyday use, the benefits to both consumers and businesses outweigh those challenges. And with autonomous vehicles already in test traversing our roadways, the day we push a button and relax and read while our vehicle drives us to our destination may be closer than we think.